For this video, we will be looking at the pH at equivalence point. So here we have acetic acid, CH3COOH. It says calculate the pH at equivalence point in a titration of 50 mils. So you have 50 mils of this, of 0.1 molar with 0.1 molar NaOH. So you're adding OH minus, and you have 0.100 molar of this. So we need to know what the total volume is, so we have to do a little bit of stoichiometry ahead of time. So let me just write the equation here. OH and H makes water. And you'll also make the conjugate base, CH3COO minus. Okay, so what we will do here is we will go to moles, and then solve for volume. Okay, so let's start with the 0.50. I'll write it here to save room. 0.0500. I move this over 3 times, divide by 1,000. 0.0500 liters of CH3COOH. I'm going to go ahead and multiply that by the molarity. This is 0.1 molar, which means 0.100 moles for every 1 liter. So the liter cancels. So this is moles of CH3COOH. I'm going to go ahead and go across using the mole ratio. For every 1 mole of this, I will need 1 mole of this. 1 mole CH3COOH, 1 mole of OH minus. Okay, so once I get that answer, which is, this cancels here. Now I have moles of OH minus. I want volume. So I'm going to go one more step. I will use the molarity, which is 0.1 molar, and write it here. 0.1 molar means 0.1 moles for every 1 liter of OH minus. This is OH minus. Okay, so this is gone. So I'll end up with liters of OH minus. When I do this math, I got 0.050 liters of NaOH or OH minus. Okay, now I'm going to do some stoichiometry. No, I'm going to figure out how much molarity I have. So here I have this together to get moles. So 0.1 times 0.05 is 0.005 moles of this. Here I have 0.1 times 0.05 liters is 0.005 moles. Oh my goodness, I have equal moles. That means I'm at equivalence point. Okay, so this is the total volume is let's see. I have 0.50 mils and 50 mils. That's 100 milliliters or 0.1 liter. So my icebox will look like this. CH3COOH plus OH minus makes CH3COO minus plus H2O. This divided by this makes 0.05 molar, 0.05 molar, 0, 0. Okay, I don't need water here. Okay, so it's going to be minus 0.05 minus 0.05 plus 0.05. So obviously they're at equivalence point, so you'll have none of these left, but you will make this. So at equivalence point, all you have in your beaker is CH3, COO minus. And you're trying to figure out what is the pH at that point. Okay, and you have 0.05 molar of this. Okay, to do that, you have to understand that this, what will that do? That's right, it will hydrolyze. So in your beaker, you have this CH3COO minus. So you have to do another icebox, CH3COO minus. Will hydrolyze. And because it's a conjugate base of a weak acid, it's a strong conjugate base, the H will go this way. And you're going to make CH3 COOH plus OH minus. So at equivalence point, you have this in the beaker. Your pH is going to be a little bit basic because you made some OH minus. So it's not pH 7, it's going to be above pH 7. It's going to be greater than pH 7. So let's find out what it is. Okay, so first you have to know how much of this you have in the beaker, which you have 0.05 molar. And you have 0, 0. You're going to make this react, you don't know how much, plus X plus X. Okay, so this is going to be 0.05 minus X and X. So the extent of this reaction depends on the Ka of the acetic acid. Actually, this is going to be the Kb. So you have to go to the appendix, find out acetic acid, which is up here. Ka is 1.8 E negative 5. Okay. So the Ka of this is 1.8 E negative 5. But right now, it's not acting as an acid, it's acting as a base, so you need to find Kb. Kb is going to be equal to 1E negative 14 divided by 1.8 E negative 5, which is equal to 5.6 E negative 10. Okay, so the equation will look like this. Kb is equal to CH3COOH times OH minus times CH3COO minus. So Kb is 5.6 E negative 10 is equal to x times x is x squared. And this is negative 10, so this will be negligible. It's going to be very, very small, but it's still something, right? 0.05. Solving for x is equal to 5.3 in negative 6. X is going to be the molarity of the OH minus. So if you log that, you're going to get POH. .28. And pH, subtract that from 14, and you're going to get 8.72. So what did you just find? You just found the pH at equivalence point. Normally, if you have both strong acid and strong base, it will be pH 7. But since you have a weak acid, the conjugate base will hydrolyze and make your solution basic. Okay. So when you look at your titration curve, your equivalence point when you have a weak acid is a little bit basic. Okay, for practice, go ahead and do this. So you have, you're looking for equivalence point again. You have NH3 this time, and you're adding H plus to it. So here's my equation, NH3 adding H plus. You have 40 mils of 0.1 molar NH3, and you're titrating it with 0.1 molar of H plus. Now I'm going to get really smart here. I'm at equivalence point. That means if these are equal, then the milliliters are also equal to get equal number of moles, okay? That's just a little bit shortcut. Otherwise, you have to do stoichiometry to get the milliliters. So when I multiply these, I'm going to get moles. I got 0.002 moles, which is going to be the same as, 0.004 moles, which is the same as this, 0.004 moles. Divide both of them by 40 plus 40 is 80, 0.08. I'm not going to do sig figs, it's just too much to write. I'll have 3 in the end. I'm sorry, I'll have 3. So this is liters. So I have 0.05 of this, 0.05 and 0, minus 0.05, minus 0.05, plus 0.05. So I'll have 0, 0, and 0.05. Okay, so that NH4 plus will hydrolyze. To make NH3 plus H3O plus. So it's going to make the solution a little bit acidic. Okay, so I'm going to do 0.05 here. 0, 0, minus x, plus x, plus x. .05 minus x. I'm going to look for the Ka of, this is the Kb. I have to convert that to the Ka, okay? So 1e negative 14 divided by, what's Kb? I think it's 1.8 e negative 5, right? It's over here. Yeah, 1.8 e negative 5. That will be Kb, which is 5.56 e negative 10. Is equal to x squared. This is going to be negligible, 0.05. X is equal to 5.27 e negative 6. Take the log of that. That is going to be my H plus already because that's x right here. Take the log of that. You're going to get pH is equal to 5.28. So at equivalence point, instead of pH 7, it's a little bit lower because you made a conjugate acid at equivalence point. Okay, last idea is the idea of polyprotic acids. Poly means many, protic means H pluses. So this acid has many H pluses. An example would be H2CO3. When H2CO3 dissociates, you're going to get H plus and HCO3 minus. Okay, so here, oh no, then the HCO3 minus will dissociate again. Oh my goodness. CO3 minus 2. So you have 2 protons, so that's why this pH curve has 2 curves. So you can see the first one starts here and the equivalence point ends here, and then that's for the first dissociation, and then the second one starts here and it goes up here. That's for the second dissociation. So here in the beginning, you have all H2CO3. H2CO3. Okay? At equivalence point, you have all HCO3 minus. In between here, when you are halfway titrating, right, you have half and half. You're going to have half H2CO3 in this point. This is very important. You're going to have half H2CO3 and half of the HCO3. Okay, so this is called the buffer region. All right, when you get to this point, all you have are so here you have the HCO3. When you get to this area right here, you're going to have half and half again of these two. This is again the buffer regions. It's pretty much like between these. So this should really be yellow on this area right here. Right? And then you keep going. This equivalence point, you're going to have equal amounts. Oh no, you're going to have all of this now. CO3 minus. Because all of them have been titrated. CO3 minus 2. So you have CO3 minus 2 here. Here you have half and half of HCO3 minus and CO3 minus 2. That's again another buffer region, and so on here. When one titrates a polyprotic acid, with the base, there is an equivalence point for each dissociation. So you have an equivalence point here and there.